Today, Pongcheng is not here, so I'm the host. Pongcheng's postdoc. Today we are happy to host Julian from Columbia University, and will present some theoretical work on the exciton condensation and the path of time-reversal-symmetry in kagome metals. Okay, can start.
All right, thanks for the introduction. So this talk is based on this paper that I did in collaboration with these three people, especially Harley Scammell, who was at UNSW and is now on the faculty at UTS, along with Tommy Lee at Free University and Oleg Sushkov at UNSW. Okay, so in this talk, I'm going to begin with a fairly elementary background on the kagome lattice and why we generally expect it to accompany interesting electronic properties. I'm then going to give a summary of the experiments that have been done in the last few years on the recently discovered family of metals AB3SB5, an interesting new set of compounds which host a variety of electronic phase transitions, including superconductivity. And the actual work of my own I'm going to talk about will begin with a discussion of the consequences of the electron and hole-like saddle points in the electronic structure of these materials and the possibility that they host an unconventional type of orbital ordering. Okay, so the kagome lattice is formed by a network of corner-sharing triangles, as shown, and inherits its name from a traditional pattern in Japanese basket weaving. The lattice is geometrically frustrated. So for instance, if I put Ising spins on this lattice and tried to align them antiferromagnetically, there'd be no way to do it. And this feature has made insulating compounds with kagome structures a popular topic in the last couple decades. So frustration combined with antiferromagnetism, which often accompanies Mott physics, means that people have long hoped that such compounds could host spin liquid states in which the spins form a long-range entangled state rather than ordering at low temperatures. Some examples include a variety of copper minerals named after various geologists and explorers. But in addition to geometric frustration, the kagome lattice has other interesting properties relevant to metallic systems. If we consider a kagome lattice with electrons free to hop from site to site, the minimal type binding Hamiltonian we get results in a very interesting electronic dispersion. So since the kagome lattice has three sublattices, if we imagine there to be a single orbital on each site, this results in three bands. And the type binding model we get, in the type binding model, we get something like the figure on the right here. So we have two bands which look quite similar to those in graphene, with Dirac points at the K points, a saddle of the energy at the M point, as well as this interesting flat band here, which results from destructive interference between possible hopping pathways. So Dirac points are sources of Berry curvature in the Brillouin zone. So the presence of spin-orbit coupling opens up a gap and results in a topological insulator. And when the chemical potential is near a flat band, the kinetic energy becomes quenched and interactions become enhanced. And so these features mean that kagome metals are a promising territory to explore when looking for interesting phases of matter. And as a result, in the last 10 to 15 years, people have investigated a number of metallic systems with kagome structures in the hopes of finding novel physics, several of which I've listed here. Most of them involve a kagome layer of transition metal atoms intercalated with some other element, usually tin or germanium, and several of these materials have been shown to exhibit interesting transport or magnetic properties. So, for instance, the cobalt tin sulfide has magnetic Weyl fermions, and I think there's an anomalous Hall effect perhaps in like the iron tin and the terbium manganese tin. Okay, so to help visualize the electronic structure a bit better, I'm going to illustrate the Fermi surface that results from setting the chemical potential to different locations in the band structure. So when the chemical potential denoted by this dashed line in the vicinity of the band crossing at K, when we place the chemical potential here, we get these small circular pockets near the K points at the corners of the hexagonal two-dimensional Brillouin zone, similar to what you get in graphene. And as we increase the chemical potential further and get something on the top right, these pockets expand in size until they grow so large that they all connect, forming a hexagon when the chemical potential cuts through the saddle point on the bottom left here. And this inscribed hexagon has corners at the endpoints of the Brillouin zone, i.e. the midpoints between the corners of the hexagon, the big hexagon. So the band structure here has a Van Hove singularity at those endpoints where the density of states diverges, resulting in an enhancement of interaction effects. And if we continue to move the chemical potential past the saddle point, the single hexagon shrinks into an increasingly circular contour converging on the gamma point at the center of the hexagon. Okay, so with those comments on kagome systems in general, I'd like to start talking about this new family of compounds discovered fairly recently at the end of 2020, so about 2.5 years ago, which triggered this major flurry of research. Unlike most of the previous examples of kagome metals I mentioned, these materials involve vanadium and antimony. So unlike iron and cobalt, which come with a strong tendency towards ferromagnetism, you might expect these materials are less likely to order magnetically, which might be desirable if you're looking for phenomena like superconductivity, which are generally antagonistic with magnetism. So these materials consist of a stack of weakly coupled layers. There's a kagome network of vanadium and antimony atoms, shown here in red, with antimony atoms located at the centers of the hexagons. Then there's a second layer consisting of a hexagonal lattice of antimony atoms where the honeycomb sites are situated at the centers of the triangles of the kagome layer underneath it. And then finally, we have a triangular lattice of alkali metals located above the centers of the hexagons indicated in blue here. So these materials are metallic, first of all, exhibiting resistivities of order of micro-ohm centimeters. They're quasi-two-dimensional, as can be seen by the fact that the in-plane resistivity is 600 times smaller than the out-of-plane resistivity. They don't order magnetically, and they exhibit a charge density wave somewhere around the 100 Kelvin mark, differing slightly between the different choice of alkali metals. And since they involve vanadium d electrons, which host multiple orbitals, in addition to the antimony atoms, it stands to reason that their electronic structure is a bit more complicated than the single band type binding model I discussed a few slides earlier. So on the right here is some R pairs, but it agrees pretty well with some DFT, which is a bit less crunchy. So I'm just going to replace it with the DFT. So we have a circular contour centered here at the gamma point, which originates primarily from the antimony atoms. And then we have three nearly hexagonal contours, as well as somewhat circular pockets located at the K points, all of which primarily result from the kagome network of vanadium atoms. So as I mentioned just a moment ago, somewhere around 90 Kelvin, depending on the material, the compounds exhibit a transition to a charge density wave order, which involves a 2x2 enlargement of the unit cell. And this is seen in STM, but also in X-ray scattering, so it's not a surface effect. And as we see here in the Fourier transform of dI/dV from real space to momentum space, the reciprocal lattice vectors associated to the charge density wave pattern are half those of the original lattice. So they correspond to the wave vectors at the endpoint, and so are naturally associated with the corners of that hexagon where the Van Hove singularity is located. So some possible candidate phases that people discussed for this type of charge density wave pattern are this thing on the left here, people call like a real or RCDW, this thing on the right here, this ICDW, which are distinguished by being odd or even under time reversal symmetry. We can think about this ICDW, time reversal odd density wave, as a pattern of circulating loop currents. So these loops of current which form local magnetic fields, where the loops themselves break the translational symmetry by enlarging the unit cell. So I don't want to necessarily spend too much time on background, but it's still worth mentioning the array of additional interesting observations that have been made. So as a function of pressure and doping, there appear to be multiple superconducting phases. So as a function of pressure, the TC of the superconductor goes up and eventually the density wave phase is suppressed, suggesting an interesting interplay between superconductivity and the high temperature ordered states. And interestingly, also, when the charge density wave is suppressed by pressure and a new superconducting phase kicks in, μSR indicates that the new superconducting phase appears to break time reversal symmetry. You can perform a spatial map of the superconducting gap magnitude, and in one of these superconducting phases, it appears that there's a component to the superconducting gap which is spatially modulated with an unusual periodicity that's different to that of the CDW. It's given by 3/4 of the reciprocal lattice vectors of the original lattice. Additionally, at maybe some lower temperature, but also maybe just at the temperature where CDW kicks in immediately, many experiments see evidence of threefold symmetry breaking. So 2 of the Bragg peaks of the CDW becoming stronger than the third, or weaker. Perhaps most exotically, near TC, people have seen some evidence of half and third flux quantization, suggesting an incipient phase consisting of charge 4e or 6e bosons, so like a condensate of quadruplets or sextuplets of electrons rather than Cooper pairs. And a lot more recently, a lot of interesting work has been done studying the massive sensitivity these materials seem to exhibit in response to applied magnetic fields and strain. So some experiments have seen that an applied magnetic field can induce anisotropy in the in-plane transport, and that the material, the appearance of these anisotropy are very, very sensitive to strain and magnetic field, that if you work really hard to isolate the sample from strain, these breaking of rotational symmetries don't appear, but even adding a relatively small strain or applied field triggers a very large anisotropy. So the main experimental question I want to draw attention to is whether time reversal symmetry is broken in these compounds or not. So as I mentioned earlier, these compounds are not magnetically ordered, but there are a variety of signatures people have seen which are strong indications that time reversal symmetry is broken. And this caused a flurry of excitement, with many theorists proposing the CDW state is the ICDW I mentioned earlier, so a periodic array of loop currents. In historical order, they were the observation of a large anomalous Hall effect, a non-trivial coupling of the density wave pattern seen in STM to an applied magnetic field, an uptick in the relaxation rate seen in μSR, and the Kerr and polar Kerr effect. So, but some of these experiments have presented a conflicting picture. So firstly, the response to the STM peaks to applied magnetic field, which was seen by the Hassan group at Princeton, was very clearly not observed by the Zelkovich group at Boston College. And secondly, many experiments which observe a μSR signal, they see something around TC at the critical temperature which the CDW appears. But really the most noticeable feature of the data appears at much lower temperatures. So somewhere around 40 Kelvin is where the relaxation rate really increases appreciably. And finally, there's the polar Kerr effect. So some groups claim they see no co-rotation, and others claim that they do, in very stark disagreement. And so taken together, time reversal symmetry breaking doesn't appear to be strongly associated to the charge density wave itself, with some samples exhibiting charge density wave and time reversal symmetry, and time reversal symmetry breaking and others not. Okay, so with that background, I'm going to start talking a little bit about theory by discussing the role of the electronic band structure in the formation of various ordered states. So a Fermi surface is unstable to superconductivity whenever there's a weak attractive interaction, but a hexagonal Fermi surface has something called the nesting property, which says that if you shift your momentum by one of these nesting vectors qi, your energy goes to minus itself. And in this situation, the Fermi surface is unstable to the formation of a density wave state with a periodic modulation of the charge with wave vector qi. And the reason for this is that it costs 0 energy to create an electron and hole separated by one of these nesting vectors, as they have opposite energies. And so as soon as there's an attraction between them, the system can lower its energy by spontaneously creating many such pairs, and the ground state becomes unstable. And so to self-consistently determine the ground state, you have to simultaneously treat the two types of ordering, superconductivity and potentially density wave order. And in a famous paper, Nankashor, Levertov, and Chubakov showed that in the simplest such model, D-wave superconductivity wins with spin density wave subdominant. On the other hand, when you have two Fermi surfaces, one of them made up of electrons and the other made up of holes, i.e. the momentum derivative of the dispersion has opposite signs on each Fermi surface, the system is unstable to the formation of a condensed state of electron-hole pairs, known as an excitonic instability. And so we can think about this can happen we can think of this as like a nesting at 0 wave vector. So I've drawn these two Fermi surfaces here separated, but I can make them sit on top of each other so that they live on at the same point in momentum space. And when we look at our nesting property from the previous slide, we have E of the electron as minus E of the hole. I can set Q to 0 and then add to this dispersion an orbital index or a Fermi surface index. So I can call one of these Fermi surfaces C and the other D. And if E of C is minus E of D, then even though there's a 0 here, so I'm considering a 0 wave vector combination of electrons and holes, I still have this nesting effect from the previous slide. But it's nesting between different Fermi surfaces at 0 wave vector. And so when this happens, there's an instability towards forming an ordered state of an order parameter of this form, CDAG D, which hybridizes the two Fermi surfaces. And this instability is strong when the areas of the two Fermi surfaces are the same, and it's suppressed when they differ, a fact I will not prove. Okay. Incidentally, this situation also arises in the iron pnictides, where there are hole pockets at the gamma point and electron pockets at M or maybe X, I don't remember. Except in that case, the electron and hole pockets are separated by finite momentum. So this leads to conventional nesting, where instead of a 0, there's a finite Q in this case. So the vanadium metals are special because, well, one of the reasons they're special is that they're a material where exactly both of the two scenarios I've discussed coincide. So the saddle points near the M point, which create these hexagonal Fermi surfaces, have opposite concavity. So if you sit slightly above one, you have an electron and one electron-like and one hole-like Fermi surface. You sit just below, you have the same thing. So to be more precise, as we move along the gamma M line, one Fermi surface goes up in energy and the other goes down. And since these are saddle points, it's vice versa as you move along the MK line. So this was shown in these ARPES results from Ricardo Comen's group at MIT. They find these 3 saddle points near the Fermi level, which have differing concavities. And the reason this happens can be understood just in a simple type binding model. So 2 of these hexagonal contours originate from the DYZ and DXZ orbitals of the vanadiums. And so if we construct a 2-orbital type binding model for these bands, then matching these type binding parameters to DFT results in something that looks like what I have on the slide here. If we denote the 2 orbitals by an index nu equals C and D, then this first term here is the hopping between neighboring sites, and then the second term here is an on-site potential. And when the on-site potential for the 2 different orbitals differs by an amount that's related to the hoppings for the 2 different orbitals, then we get something like this middle panel up here. We get we get what kind of looks like two copies of the tight binding model for a single Kagome lattice, shifted so that the like valence band saddle point of one set of orbitals is nearly degenerate with the quote unquote conduction band saddle point of the other. So we have something here where we have at M a red and a blue saddle point that have opposite concavity. And there's some subtlety that I probably won't discuss too much, which is these saddle points get called M-type and P-type. And the M-type one originates from the like valence band saddle point of like if we look at this red like collection of bands, and the P-type originates from the conduction band saddle point, so to speak. And they're so called because the Kagome lattice has this funny property where the wave functions near a P-type Van Hove singularity have support only on one sublattice, and at an M-type Van Hove singularity, the wave function has support spread out over two sublattices. But this is not going to play a key role in what I'm going to discuss. Since I'm arguing the appearance of multiple Van Hove singularities is important, I'd like to elaborate somewhat more on the details of these saddle points. So the two Van Hove singularities which arise from the XZ and YZ orbitals are denoted as K2 and K2 prime, appearing in bold red and blue in this plot. So K2 is the M-type and K2 prime is P-type. And then in addition to these, there's another Van Hove singularity that originates from the dx squared minus y squared and dz squared orbitals. And that's this pale red one, which gets denoted as K1 and contributes another P-type Van Hove singularity beneath the Fermi level. And there's some difference between the cesium-based compounds and the potassium rubidium, which has to do with the different interlayer spacings between the three compounds, which means that the ordering of the K2 and K1 Van Hove singularities is swapped in cesium compared to potassium and rubidium. This plot I've shown here is what the band structure looks like for cesium. So K1 is a little bit closer to the Fermi level actually than K2. K1 disperses somewhat more in the KZ direction, whereas K2 prime and K2 are fairly nested and do not disperse much in the Z direction. And the fact that K2 and K1 are swapped around for cesium compared to the other two likely plays a key role in the fact that a number of the novel features seen in the cesium-based compounds are absent in the potassium and rubidium. Okay, so with this setup, we're now going to follow the standard approach for describing interacting Fermi surfaces near a Van Hove singularity, where we write an effective theory restricted to the near vicinity of these points on the hexagon we call patches, these corners of the saddle point Fermi surface where the density of states diverges. And to depart from the classic treatment where a single interacting hexagonal Fermi surface is treated, I'm now going to take two, which have opposite concavity. So we might think of this model as, for instance, we've taken the K2 and K2 prime Van Hove singularities, and we're going to look at interactions between them. For the sake of sanity, I'm going to deal with two rather than three Van Hove singularities. But I could have also, for instance, taken K2 prime and K1. And because they originate from orbitals with different angular momentum Z, MZ eigenvalues, the resulting orbital, the resulting order parameters you get from hybridizing, say, K2 prime and K2 versus K2 prime and K1 will have subtly different symmetry properties, but we're just going to leave that aside and consider this abstract problem of two interacting hexagonal Fermi surfaces, something like what I've drawn on the left here. So I'm going to assume that the two Van Hove singularities are pretty much exactly degenerate for the sake of simplicity, but this is not exactly true, as one can see from the band structure plots on the previous slides. And non-degeneracy of the Van Hove singularity translates to slightly different areas of the two hexagonal Fermi surfaces, which works against excitonic order. As I'll discuss a little more somewhat later, however, uniaxial strain actually moves both Van Hove singularities closer to the Fermi level, and so this should actually promote excitonic order, one might think. Okay, so if we denote the fermions corresponding to one Fermi surface by C, and the fermions corresponding to the other Fermi surface as D, we have something which looks like this. We have kinetic energy for the C fermions is some energy that has a saddle point form, and then, oh, okay, there's some sort of visual glitch here, but we have minus the same energy for the whole like Fermi surface. So we have three distinct corners of these hexagons, which we call patches, and corresponding to the three endpoints. And we're going to index these by alpha. So alpha equals 1, 2, 3, index the 3 points on this hexagon. And then we write down all possible interactions between these two Fermi surfaces that scatter you between the patches and between the two Fermi surfaces. So we write down everything that's allowed by momentum conservation, which gives you this, which is not very enlightening, but that's the full expression. I won't force you to keep looking at it, but roughly speaking, they look like the arrows shown on the right here. So we can have couplings which, like these blue lines, which keep us within the same patch on the same Fermi surface. We can have umklapp scattering between the two Fermi surfaces. We can have scattering that puts one fermion to the other and takes one from D to C and another from C to D, and so on. And then lastly, we write down all possible order parameters which the system is unstable towards. So as in the ordinary problem of a hexagonal Fermi surface, we have an instability towards charge and spin density wave order and also superconductivity. But in this situation, which got called a twofold Van Hove singularity, we get three additional weak coupling instabilities. So we have excitonic order that's spin singlet and triplet, which is the hybridization between the two Fermi surfaces that I described before. And interestingly also, it's probably not relevant to these materials, but in this model, a pair density wave, a spatially modulated superconductor, appears as a weak coupling instability. So ordinarily, a pair density wave, so forming a superconductor where the Cooper pairs are on different corners of the hexagon, usually this is disfavored by the fact that fermions on different corners have opposite energies, and superconductivity likes to take place between fermions with the same energy. But if you consider fermions on different corners and different Fermi surfaces, that pair of fermions will have the same energy. And so actually there is a weak coupling instability towards a superconducting state that's finite momentum, which is kind of novel, but it probably doesn't relate to the pair density wave seen in these materials, because such a pair density wave would have a wave vector that's half of the reciprocal lattice vectors of the original lattice. So its momentum would be, its wave vector would be given by m, but the wave vector of the pair density wave seen in these materials is 3/4 of the original reciprocal lattice vectors. So it's probably a different pair density wave at play in the materials. Okay, so we have all possible couplings allowed, we have a kinetic term, and we have some possible order parameters. So what do we do with all this mess? So to determine the dominant ground state at low energies, we use the perturbative renormalization group procedure. So we start with some cutoff lambda around these patches, and then we progressively lower this cutoff, integrating at electrons in some shell, and then iteratively getting closer and closer to the Fermi surface and seeing how the effective couplings evolve. And so we get these differential equations which describe how the effective couplings evolve as we lower our cutoff. And then as we do this, we track how the susceptibilities towards various order parameters evolve. And if a susceptibility diverges, it means that the system is unstable towards forming an ordered state with that order parameter. The one which diverges the fastest is the dominant ground state. So we take our possible order parameters on the previous slide, and we get a set of flow equations similar to the ones for the couplings that tell us how the susceptibilities of these order parameters evolve. Yeah, the time, the DDT in these flow equations is essentially the cutoff divided by the temperature. And so lowering the cutoff is actually equivalent to starting with some UV cutoff and considering, and then considering the physics at temperatures comparable to the cutoff, and then lowering the temperature and asking what the dominant ground state at that temperature is. So the main takeaway from this slide is that the renormalization group flow is the same as lowering the temperature, and these flow equations will tell you that at a certain temperature, the couplings and susceptibilities may diverge, resulting in a new ground state. Okay, so we can analyze these equations in two different ways. On the one hand, we can make some universal statements. So generically, this renormalization group flow, where you ask what happens as you lower the temperature and you see what the effective couplings do. So this will generically result in the effective couplings diverging, but they diverge at fixed ratios of each other, which we refer to as fixed rays. And so there are actually only a finite number of possible stable fixed rays at long RG times, which you can access by analyzing the asymptotics of these differential equations. And so these fixed rays are like attractors of this system of differential equations, and we can simply enumerate all possible long RG time behaviors, which will tell you all possible weak coupling solutions to the model. But we only reach long RG times if our couplings start out sufficiently weak that we flow for a long time before a susceptibility diverges. So you start at some high temperature and you lower the temperature for quite a while before anything diverges. But if the couplings are sufficiently strong to start with, an instability can appear before you reach the long RG time limit, and so the system then isn't characterized by a fixed ray. And in this case, we can take a different approach, which is to match the initial values of our effective coupling constants to DFT results, and then plug those into the RG equations and explicitly solve them and see what they predict. So we have these two possible approaches to analyzing the model. So we'll discuss both approaches. And skipping over some details, we looked at this model for both kagome and honeycomb systems, and also experimented with adding asymmetry between the electron and hole Fermi surfaces. But the upshot is that in all cases, we found a set of fixed rays that included singlet and triplet S and D wave excitonic order, as well as D wave superconducting states similar to those found in the Chubukov paper. And I'd now like to spend a bit of time discussing the properties of these orbital orderings. So the one we focused on in the published paper was the D wave solution, but there's actually an interesting collection of orbital orderings. So the D wave solution consists of these two degenerate possible order parameters, where the entries of this row vector correspond to the values of the order parameter on the three patches at the three corners of the hexagon. And if we continue these order parameters around the Fermi surface, we can think of these two states basically as being like cos 2 theta and sine 2 theta, where theta is the momentum angle. And they can in general also have an overall complex phase, which I've called phi A and phi B. And the fact that they correspond to cos 2 theta and sine 2 theta is why we call these D wave, even though it's far from obvious in the threefold symmetric form, this row vector. And so we can explicitly take our couplings from the DFT results and integrate the flow equations, and we get something like this. So these are basically plots of the order parameter susceptibilities as a function of RG time, which is inverse temperature in units of the cutoff. So left to right is lowering temperature. And some of the couplings actually vanish if we take values from ab initio results. And this has to do with the M-type versus P-type story for the Kagome lattice I mentioned earlier. So we also played around with giving some of these constants small negative values, potentially coming from phonons. But with some physically reasonable numbers and stopping the flow around 100 Kelvin, we got a charge density wave phase, which was the leading phase, closely competing against singlet and triplet excitonic order. And if the couplings were hypothetically weaker and the RG flow lasted longer, eventually excitons would kick in. But at intermediate coupling strength, the charge density wave order is the first to kick in. So I'd like to spend a little more time teasing out the phenomenology of the D-wave excitonic phase. So we have two degenerate D-wave states for these excitons, phi A and phi B, and the actual ground state is some combination of these. To determine which combination is the favored state, we compute the Landau free energy as a function of the two order parameters, which were capital phi A and phi B, and recall that lowercase phi A and phi B were the complex phases of the two order parameters. And we get this expression. Now, if we chose a ground state which was just one of phi A or phi B, we would get a nematic state which spontaneously breaks the rotational symmetry. So a ground state that goes as cos 2 theta or sine theta. But in the absence of coupling to any other external probes, when we just look at the free energy here, we find that this thing is minimized by creating a relative phase of pi over 2 between the order parameters. So creating this D plus ID fully gapped combination of the two order parameters, which spontaneously breaks time reversal symmetry because of the I in front of this sign here. So this state is called D plus ID or chiral D wave, and it's the leading excitonic condensate in the absence of coupling to strain or other perturbations. Now, ordinarily, we think of time reversal symmetry breaking in terms of the situation I just described. We have a multi-component order parameter and therefore something which transforms non-trivially under the spatial symmetries. And then we take a complex combination of these two components and get something odd under time reversal. But perhaps something which is perhaps rather surprising at first glance is that we're perfectly allowed to have time reversal symmetry breaking S-wave excitons, i.e. an order parameter that's in the symmetric A representation because of the multi-orbital nature of these order parameters. Specifically, I can make something which is proportional to sigma y in orbital space, but is nonetheless S-wave in this patch theory. So I can have an order parameter that looks like something what I've got on the slide here. So similar to how we have the possibility of R and I CDW, we can have R versus I S-wave excitons. You might hear people say there's no way that to have time reversal symmetry breaking if a possible order parameter belongs to the A representation. But one of the takeaways I'd like to impart from this talk is that actually that's not true, and S-wave orbital order quite naturally appears in this setting. And this shouldn't be all that surprising. What I'm describing is essentially identical to just a Chern insulator. This might have relevance to some of the experiments that have been done on these materials around about the 40 Kelvin range, which give evidence of some phase that kicks in that transforms in the A representation. So there are these elastoresistance measurements and the magnetochiral anisotropy that I mentioned some slides previously. The fact that this thing is rotationally and translationally invariant means that it couples at linear order to an applied magnetic field. So it's highly sensitive to applied fields, consistent with the sensitivity of this A state that appears around 40 Kelvin. And I should comment this mechanism for creating something time reversal odd out of an anti-symmetrization in orbital space also gives a mechanism for time reversal odd nematic order. So I could have taken the cos 2 theta, for instance, from a few slides ago and stuck a sigma y on it. So that's an interesting possibility, but I won't explore it further in this talk. So we know from experiment and also from our explicit integration of the RG equations that charge density wave order appears at higher temperatures than anything else in these systems. So we naturally have the question of how does the excitonic state interplay with the charge density wave? And to answer this question, we have to use the same formalism as before, i.e. we calculate the Landau free energy, except now we have a non-zero charge density wave order parameter as well as the excitonic order parameter. And so the free energy gains these two additional contributions, one purely from charge density wave and the other from coupling between excitons and charge density wave. And this expression looks a bit messy, but basically C alpha beta is the charge density wave order parameter formed by coupling electrons of patch alpha and patch beta. Phi alpha is the value of the excitonic order parameter at patch alpha. And this V inverse thing is the coupling which drives the formation of the charge density wave state. And after we perform the non-trivial task of computing these coefficients, basically numerically, this C2 is roughly half of the other C constants, which are all roughly equal for a range of temperatures. And by doing some basic algebra with this quartic form, one finds that in this range of temperatures, the minimum of this potential always consists of both non-zero charge density wave and non-zero excitons. So the takeaway message from this slide is that if you look at the minimum of the free energy, you find charge density wave sets in at some higher temperature, and then at lower temperatures, you get a coexisting phase of excitons and charge density wave. So long as the couplings in the quadratic term, this V inverse and the lambda from the previous page, this coupling here that drives the excitonic order, so long as these couplings are comparable to each other. So that excitons are nearly degenerate with charge density wave. So we can visualize this nicely in these phase diagrams. We chose to separately investigate two scenarios. So we looked at both choices of initial parameters, which resulted in a real charge density wave and an imaginary charge density wave, and we found this picture. As you vary the coupling constants, like that V inverse and that lambda, around the values that you would get from ab initio calculations, you get these top two pictures, and we see there's a wedge in the phase diagram where the two phases coexist. And when we explicitly integrate the RG equations using the plots I showed a few slides ago, we get this heuristic phase diagram at the bottom where at high temperatures, we have the metallic normal state in dark blue, and then a charge density wave in a region of coexistence. So basically, this is just a visual representation of the takeaway of our previous slide. I'd like to comment somewhat further on the phenomenology of the D-wave states, of which there are two degenerate orders. So as I mentioned, individually, these order parameters are nematic states, which break threefold rotational symmetry. The signatures of these in real space is something like what I've plotted on the left here, where we have a pattern which preserves the translational symmetry of the lattice, but breaks its rotational symmetry. And then the chiral combination, the D plus ID solution, gives us something that looks like what we have on the right here, something which preserves rotational symmetry as well as the translational symmetry of the lattice, but consists of these circulating loops of current within the unit cell. So we have this intra-unit cell type of circulating loop current, kind of similar to the Varma model of the pseudogap in the cuprates, but this is in some ways a simpler structure of order parameter. There are other complications in the case of the cuprates. I wanted to make some comments on the 166 kagome metals as well. So this is another kagome metal that's been studied very closely recently. So these are a bilayer kagome motif with very similar Fermi surface structure and also exhibit a charge density wave, but the charge density wave is very different in these compounds. It involves a √3 by √3 enlargement of the unit cell. And so the wave vector of the charge density wave is associated to the K points rather than the M points. Earlier in this year, ARPES data were published on these kagome metals, and they found the same feature of opposite concavity saddle points that I described earlier. In fact, the opposite concavity Van Hove singularities are more robust in these materials than in the 135 materials I've discussed so far, because of the fact that the charge density wave gap stays well away from the Van Hove singularities. So this feature of the opposite concavity saddle points isn't really disrupted or competing at all with the presence of charge density wave order, which makes it much easier for orbital ordering to appear at lower temperatures than the charge density wave. And so, yeah, there also seem to be some indications of time reversal symmetry breaking in these compounds. There was a MUSR experiment reported earlier in the year, shortly followed by transport. And so it's interesting to consider the possible interplay of nematic or chiral excitonic order in these materials, and their response to strain in applied fields is essentially unexplored. So I would like to conclude by making several comments about experimental attempts to distinguish orbital and charge density wave order. So we know that strain, pressure, and doping move the chemical potential around, and strain can move one Fermi surface away from the Van Hove singularity while keeping the other nearby. So to be somewhat more specific, ab initio calculations indicate that applied pressure does something like what I've drawn in the middle here. So it pushes the Van Hove singularities away from the Fermi level, but for some range of pressures does so in a symmetric way, so that the area of the electron and hole-like Fermi surfaces stay the same. So you would think that this should tend towards suppressing charge density wave order, but is less antagonistic towards the excitonic orbital instability, so long as the area of these two Fermi surfaces stay similar. Uniaxial strain has been shown these are ab initio calculations, by the way, this is DFT. So uniaxial strain has been shown to move all three Van Hove singularities closer to the Fermi level, which should complicate things, since the fact there are three Van Hove points to contend with probably becomes increasingly unavoidable. But you might also expect that this should enhance the tendency towards excitonic order. It's known that the charge density wave gap actually only appears on one of the Van Hove points and not on the other two. So it would be interesting to study the orbital structure of the charge density wave in ARPES as a function of strain, and see if strain allows a pair of ungapped opposite concavity Fermi surfaces to appear more reliably near the Fermi level. And biaxial strain appears to produce something that looks like the far left here. So selectively pushing one Van Hove singularity further away from the Fermi level while pushing the other closer. And so initially, this should suppress excitonic order and more or less retain the tendency towards charge density wave. Although it appears that for very large tensile strain, you can actually push one of the p-type Van Hove singularities beneath the Fermi level above, which looks like it could potentially create another twofold Van Hove singularity for large enough strain. So I just said a whole bunch of words, but the message is really that the effects of strain are actually rather complex in these materials, since the location of the Van Hove points seems to be quite sensitive to it. So, for instance, on the one hand, a nematic order should, for example, couple to applied strain, and yet on the other hand, strain rearranges the Fermi surfaces, which may or may not suppress the tendency towards orbital or excitonic order. So I'd like to make the point that not seeing nematic order in, say, elastoresistivity doesn't mean it isn't there, as the Fermi surface evolves sensitively as well. So optical probes, for example, are perhaps a clearer smoking gun. And many approaches to current experiments have analyzed how charge orders interplay with strain using Landau-Ginzburg theory, but these approaches will neglect the crucial effects shown on this slide. So one of the takeaway messages I'd like to push in this talk is that those approaches must be complemented with an ab initio analysis of how the Fermi surface evolves, as this plays a crucial role in how order parameter instabilities themselves evolve. But the influence of strain and pressure are definitely worth further study to see if time reversal symmetry might be disentangled from charge density wave order. As far as I'm aware, the Philip Moll's recent experiments have looked at the role of strain in time reversal and rotational symmetry breaking, but pressure is less analyzed. I don't know if those experiments are slightly harder. It's worth commenting that actually the MuSR people at PSI did manage with difficulty to take data in a strained sample, though I'm not sure it's published yet. My understanding, if I remember, is that the conclusion was that they saw an enhancement of the signal they see at temperatures around 40 Kelvin, but the feature they saw at the charge density wave temperature was more insensitive. But since I couldn't find their paper online, I'm not familiar enough with the details of their setup. So as I mentioned, strain and pressure have a somewhat complicated effect in these compounds because the location of the saddle points is very sensitive to them. Something I'm a bit more interested in is the possibility of looking for optical probes of the excitonic state. So because the excitonic state is formed between electrons and holes at the same momenta, there is zero momentum order parameter, unlike the charge density wave, which necessarily has a wave vector corresponding to the periodicity of the charge density wave. And so this is a familiar situation in many semiconductor systems, such as TMDs, where you can have a pairing of excitons within a valley or between different valleys, which get referred to as indirect or bright versus dark. And bright excitons should have some sharp optical signatures, since light is always Q equals 0 compared to condensed matter momentum scales. So this has a number of implications. First, that when we approach the temperature at which orbital order appears, a peak should appear in the intensity of Raman scattering, which can selectively probe for fluctuations in a given symmetry channel. And moreover, when the excitonic order sets in, it should couple strongly to the optical phonon spectrum. So observing a splitting in, say, the E2 phonons at temperatures less than TCDW would be a strong indication of the presence of excitonic order. So to conclude, the kagome 135 metals exhibit a rich array of interesting electronic phases. A point which is relatively unemphasized and underexplored is that these materials feature degenerate electron and hole Fermi surfaces. And in this situation, a type of orbital order which hybridizes the two Fermi surfaces, this excitonic condensate, appears naturally as a weak coupling instability. And this phase, apart from the charge density wave, with its potential to break time reversal, could possibly resolve some puzzles related to apparently contradictory experiments. So thank you for listening to my talk.
Very nice talk. Yeah, thank you. So now it's time for the questions. Fang, you can unmute yourself and ask.
Hi. Hi, Julian. Very interesting talk. So I'm wondering, what is the excitation like band structure of this excitonic condensate? Is it still metallic? Because usually I would expect an exciton condensate would give you an insulating type of band structure.
Yeah, it should gap out the endpoints. If two Van Hove singularities that are degenerate then hybridize this way, then they'll disappear and gap out. That's right.
Oh, okay. So the ground state at this certain temperature you would expect it's becoming some sort of an insulating state.
Well, there are other the Fermi surface at gamma, for instance, would remain ungapped.
Oh, okay.
So there are other parts of the Fermi surface that would remain metallic.
Okay, thank you.
Ming? We cannot hear you.
Hello?
I mean, we cannot hear you.
Hello?
We can barely hear you.
Okay, sorry.
Oh, we can hear you now. I think we can hear you now.
Sorry. So, Julian, can I ask? I might have missed this point. So this excitonic constant state phase is decoupled from the CW order, right? Or they don't have to be intertwined. And is there a understanding of does one necessarily have to be occurring at a higher temperature than the other, or what is the relationship between these two orders?
Yeah, there's no necessary hierarchy in the critical temperatures. That's not something I can predict. It's kind of impossible to predict TC of an ordered state from theory. So we took values that were motivated by the results of ab initio calculations, and we got a phase diagram that looks like the one that I showed, but there's no theoretical reason why one should come before the other. In fact, in the model I presented, there shouldn't be a large hierarchy, and there's no reason why you would think that there should be a large ratio between their critical temperatures.
Okay, thank you.
Julian?
Hi, very interesting talk. So kind of related to Ming's question, in the scenario where exciton order has a lowering critical temperature than the CW, then at the point where exciton order develops, you already have a reconstructed Fermi surface, and then the endpoint is gapped. Could you comment on that?
Yeah, I neglected that effect. So if the band reconstruction is very strong, then you have to carefully work with reconstructed bands. But the treatment that I presented in this presentation assumes that the effect is weak. In ARPES, it's seen that the charge density wave gap only really appears on one of the Van Hove points, and the other two are kind of left untouched. So that would be like maybe some motivation for such an approach that, okay, maybe applied strain as well takes the two Van Hove points that are ungapped by the charge density wave and maybe pushes them closer to the Fermi level. But yeah, like a more careful treatment of what happens when you include the charge density wave on one of the Van Hove points is not in this talk. It's something I could look into, but yeah.
But in principle, when the exciton order develops, it still gap out the endpoint, right? Yeah. So ARPES should be able to see that.
Yes, that's right. Yeah.
Any other questions? Ming,
can I ask a follow-up question? Okay, Julian. So can I ask you mentioned this excitonic constant state order would break naturally time reversal. Is that correct? That then can you comment on what do you expect to happen to the bands under a magnetic field?
Applied magnetic field. So it depends on whether the coupling to magnetic field depends on whether the excitonic state is S or D wave. So S wave couples more sensitively to applied field than D because it can appear at lower orders in the free energy. What happens to the bands themselves, the dispersion? I couldn't say just off the top of my head, but
okay.
Yeah, I'm not sure, but something happens if it breaks time reversal. Yeah.
Okay, thank you.
Any other questions? Okay, if not, let's thank Julian again. Yeah, we're next talk. I think we'll have one last talk next week, and hope to see you next time. Thank you.
Thanks.